So hello and welcome to this fifth lecture in this series. In the last lecture we looked at LCAO, linear combination of atomic orbital theory, and we thought about how we could build up molecular orbitals for molecules. And now once we've got our orbitals, we need to put our electrons into them, and this will give rise to a number of different electronic states. So now we need to be able to describe these electronic states in terms of molecular terms. So what we can do first of all is let's think about H2. So we're going to, if we think about the different orbitals that we've got, so we've got the 1s orbital from atom 1 and the 1s orbital from atom 2, and then for the hydrogen atom the p's and the s's all have the same energy. So here are the 2s and 2p orbitals, so again 2s and 2p over here, and we can now generate the molecular orbitals from these atomic orbitals. So we can generate two orbitals based on our 1s orbitals, and then we can generate other orbitals from our 2s and 2p orbitals. So what happens is we get a low energy orbital there, we get two there of the same energy, then another one here, two here, and the last one. So just join those up. There we go, we've got our molecular orbital diagram for H2. So we need to think just a little bit about what these orbitals are. So the 1s ones are easy to understand. So this is the 1s sigma, and this is a 1s sigma star. The next one here is it's a sigma orbital, but generated from the p orbitals which are along the axis of the molecule. So this is a 2p sigma orbital. These next two are the 2p pi orbitals, and then these two in the middle here are the 2s sigma orbitals. So 2s sigma star for those two. Then the next ones up are the 2p pi star, and this last one at the top is a 2p sigma star. So these are our molecular orbitals, and we can imagine now putting electrons in. We've got two electrons to play with. We can put these two electrons into these orbitals, and this will generate a whole range of different electronic states. So we need to be able to define these. If we draw an energy diagram, so we've got energy here, and we've got bond length across the bottom. We know that if we have both electrons in the lowest orbital, then we've got our standard ground state of hydrogen, and we can draw. Let's draw it like this. So we've got to draw a Morse curve representing this state, this electronic state. If we have one electron in the 1s sigma and one electron in the 1s sigma star, this will give us another state which has its anti-bonding character, so it'll be about there on the diagram. But then we can start putting electrons into our, we could keep one electron in our 1s sigma, and then we could put the second electron into our 2p sigma, or a 2p pi, or a 2s sigma, and this is going to give rise to a whole new set of electronic states at higher energy. So it's not very well drawn, but you get the idea. There's curves there. So there's a whole series of different electronic states available just for the hydrogen molecule, dihydrogen molecule. So we need to be able to distinguish between these different electronic states, and then to be able to work out whether we're allowed transitions between them, and so on. So that's what we're going to look at in this video podcast. Okay, so if we put electrons into molecular orbitals, now this argument here is for diatomic molecules only. We need to think about the various quantum numbers involved. So we've still got L and S again, so capital L and capital S, so representing the total orbital angular momentum and the spin angular momentum. But once you go to molecules, once you go from atoms to molecules, we've got two nuclei, and these two nuclei are going to generate a significant electric field within the molecule, which is going to affect how the electrons behave. And actually this electric field caused by the two nuclei is going to dominate everything in the molecule. And this electric field couples strongly to the orbital angular momentum. So it means we can't really use L anymore. We now need to use a slightly different quantum number instead. We use a lambda. And this is the component of the angular momentum along the internuclear axis. So we use a little lambda for thinking about the orbital angular momentum along the internuclear axis for individual electrons within the system. And lambda's a slightly different quantum number. It's effectively equal to, equivalent to Lz, but it's the magnitude of Lz. So lambda only takes positive values, so it can have the values 0, 1, and 2, and so on. So let's have and we can now then combine these little lambdas for individual electrons to get a capital lambda, which represents the total orbital angular momentum along the internuclear axis of the molecule. So let's have a look at the different things. So we had, if we go back to thinking about Lz or ML, as we've actually been using for most of this course, this can take values 0, plus and minus 1, plus and minus 2, plus and minus 3, and so on. Lambda, so our new quantum number, which is the axial component of the axial component of the orbital angular momentum. This takes the value 0, 1, 2, 3, and so on. And as with L values, we can correspond these lambda values to states, to letters. So instead of using S, P, D, F, now we use sigma, pi, delta, and phi. So if we have now an electron in an orbital, say, with lambda equals 1, this is a pi orbital. This is because it's created from orbitals which have ml of plus or minus 1, so the p orbitals of the atoms. So now we can actually see where the labels of sigma and pi come from when we describe orbitals in molecules. Now we can combine, once we've got a system with a molecule with several electrons in, we have to combine these lambda values, these little lambda values, to give us our capital lambda values. So capital lambda here, and this is basically the sum of the individual lambda values. This one's actually a straightforward one to work out. In this case, it's just the sum of the components. So you remember when we were coupling, for example, L and S, we had integer steps between the sum and the difference. Here it's just the vector sum of the individual components. And again, if we have a state which has lambda of different values, so lambda could equal 1, 2, 3, and so on, and we can now give these individual states a letter. So we use capital sigma, here we use capital pi, here we use capital delta, here we use capital phi, and so on. You'll have noticed up here that lambda is only positive numbers, so that means there's some degeneracy which comes in. So if lambda equals 1, then this is going to be twofold. This is going to be twofold degenerate, because it's going to be the terms which were going to be ml equals plus 1 and minus 1. So if you go back down to the bottom here, we can see there's going to be degeneracy. So the sigma is going to have a degeneracy of 1, but all the other states are going to have degeneracy of 2. Okay, so now we've seen our L and M. We now need to think, our lambda and our L's and little lambda, capital lambda. Now we need to think about the spin. In fact, the spin is treated very much in the same way as it is for atoms, and that's because the spin angular momentum of electrons couples only very weakly with the electric field along the internuclear axis. So we don't need to. That doesn't really change things very much. But occasionally it's sometimes necessary to calculate the component of the spin angular momentum along this axis, and then we end up with a quantum number sigma for one electron, little sigma, sorry, and then capital sigma for many electrons. We can actually couple then our lambda with our sigma to give us our total axial component of the angular momentum omega. This is a capital omega, so this is equal to the magnitude of lambda plus sigma. So for molecules, omega is the equivalent of J, capital J, for atoms. I'm not going to say too much about omega values in this course. Let's not worry about that too much. Now we've got all these components, we can actually write a term symbol for molecules. So as before, we've got the multiplicity top left, then we've got the capital lambda number, which gives us the total orbital angular momentum, and then we've got our omega value, which is the coupling of the orbital angular momentum and the spin angular momentum along the internuclear axis. So this means if we have a molecule, we can put the electrons into the orbitals and then work out the available electronic states. Now, there's a few more labels which we need to look at very briefly, and these are labels plus, minus, G and U. So sigma states, there's a little bit of extra nomenclature. They can be either defined as being plus or minus depending on the symmetry of the wave function with respect to a plane in the internuclear axis. And then we also have a G and a U, which we can use only for homonuclear diatomics. They only apply for those, and this depends on the symmetry of the orbitals with respect to the centre of inversion. You can remember that if we have a sigma orbital, so we've got two nuclei, one here and one here. If we take a point over here and then go through the centre of inversion down to over here, if it's the same sign, then it's going to be G. And if we had, say now we have a sigma star orbital, so with the two nuclei there, we take a point here, I'm going to take a point down here, and here we can see that we'd change sign. Let's shade in one of these. We'll change sign when we go from one side to the other, so this is U for Ungerade. So this gives us a whole load of states, so we can have term symbols like for example, singlet, sigma, sigma G plus. Another state might be triplet, sigma U minus. Whoops, sorry, that's a minus sign there. We can have singlet pi states, quartet pi. We can have singlet delta G, and there's all sorts of states which can arise from the electronic configuration of the molecule. This all works for diatomics. If we now go to polyatomic molecules, things are made a little bit simpler. So, and in this case, electronic states are given in terms of the total electron spin, so we need to think about the multiplicity, whether it's singlet, triplet, and so on, and then the symmetry of the wave function within the point group of the molecule. So if we have a molecule like a O3, so we know the shape of this molecule, so this shape, so it's in C2V symmetry. The ground state of this molecule is a singlet A1. So singlet because all the electrons are, it's a closed shell molecule, and A1 because the symmetry of this electronic state has A1 symmetry. If we have some other molecule, let's have a slightly more exotic molecule, so CH2. So this is a radical species. You can imagine it's got 2 dots on it here, and this is a triplet B. The ground state has triplet B1 character, and so on. So triplet because the electrons are, there's 2 unpaired electrons, B1 because the symmetry of the electronic state has B1 symmetry. So now we need to go on and apply this to an example. So let's have a look at the dihydrogen molecules, nice simple case to start with. Let's think about the ground state of H2. So the ground state of H2 has 2 electrons in the 1s sigma g orbital, and we've drawn the molecular orbital diagram before. So we've got the 2 1s orbitals which combine in linear combination to give a 1s sigma g orbital and a 1s sigma u star orbital. Okay, so now we can put our 2 electrons in, so they're going to go into the ground state here. So now we can start working out what values we need for our term symbol. So first thing is we've got 1 spin up electron, 1 spin down electron, so that means capital S overall equals 0. So that means we've got a singlet state. Okay. Now we need to think about the lambda values. So lambda 1, so the first electron is in a sigma g orbital, and so this is going to have a lambda value of 0 because there's no it's made from s orbitals, so there's no orbital angular momentum, and the other electron also comes from an s orbital, so lambda 2 is also equal to 0. And if we have, so because lambda and lambda 1 and lambda 2 are equal to 0, this means that our capital lambda is also equal to 0, which means we have a sigma state. Last thing we need to do is think about just the symmetry of the molecule of the orbital. So if you draw a plane, let's draw the so this is just a plane, and this is the molecular orbital, so it's going above and below the plane. So the symmetry of it, so with reflection in the plane, it's the same above and below, it's symmetric, so this gives us our plus state. And if we now think about the centre of inversion symmetry, we've got our molecular orbital, which looks a bit like that. They're the 2 nuclei. If you go from one point here down to a point over here, it's the same phase, so it's going to give us a Gerada configuration. So if we put all this together, we get H2 in its ground state is going to be a singlet sigma g plus state. So that gives us our answer. Let's have a look now at one of the excited states of hydrogen. Let's do hydrogen in the 1s sigma g. Let's have 1 electron in the lowest energy orbital, and let's put 1 orbital into the 2p pi u molecular orbital. So if we drew our energy diagram again, we've got our s orbitals, 1s, and then we've got our 2s and 2p all together. Then we can combine them to form our molecular orbitals. Here we've got 1, 2, 1. Yep. Okay, so now we can put our electrons in. So we're putting 1 in here, and we're going to put the other electron in these orbitals here, the 2p pi u orbital. So it's a bonding orbital made from either the 2px or the 2py orbitals, if the internuclear axis, of course, is the z-axis. Now let's need to work out our various quantum numbers. So we can see one electron is spin up, the other one is spin down. So that means our capital S equals 0. So again, we have a singlet state. Now we need to work out what our lambda values are. So lambda 1, let's think about the electron in the 1s sigma g orbital. This is an orbital made of from s orbitals, so it has a lambda value of 0. The other electron is in an orbital which is made from p orbitals, so these have an L of plus or minus 1. So well, an L value of 1, sorry, so a lambda value of 1. So we can combine these to give us our capital lambda value, and this, the only value we can get from combining these, is 1. So this is going to give us a pi state, so capital pi. Now if you think about the symmetry of the orbital, so if we think the two nuclei sort of here and here, the orbital looks a bit like that. So if we now look at the inversion point going from here to here, going from here to here, we can see it changes phase, so it's going to be an Ungerade state. So we combine these, and this gives us, in the end, we get a singlet pi U state for a hydrogen in one of its excited states. Okay, so that gives us an example of how we can work through these cases. Now I've got some homework for you to do. So to work out the possible electronic states, so I work out the term symbols for NO and N2 in their ground electronic configuration. So that's something for you to have a go at. Next thing, once we've got these electronic states, we need to think about what order they go in. So then basically you can use Hund's rules. So I've got an example now of O2, so if we use the ground electronic configuration of O2, we can get 3 possible electronic states. So you've got a triplet sigma G minus, a singlet delta G, and a singlet sigma G plus. So we just need to put these in order. So Hund's rules say first of all the states with the highest multiplicity are lowest in energy. So therefore, if we draw a diagram now with energy going up here, the lowest energy state is going to be the 3 sigma triplet sigma G minus. Then somewhere up here, well, the next thing is the ones with the highest value of L or lambda are next. So in this case, it's the singlet delta G state, because delta corresponds to an L value of a lambda value of 3. Sorry, a lambda value of 2. And then finally up here we've got the last state, so the singlet sigma G plus. Okay, so now we know we've got the tools, the equipment to work out electronic configurations, hence work out electronic states, and then put these states in order of energy. Now we need to label these states, and there's various conventions in spectroscopy, and so one of these is that the ground state is often labelled as just X. Then excited states of the same multiplicity are then labelled in just letters of the alphabet starting from A. So you go then A, B, C, and so on. These are going to be excited states of the same multiplicity as the ground state. If we have states of a different multiplicity, so we can imagine for dihydrogen, the ground electronic state is a singlet, but there are also triplet states available. So if we have states of another multiplicity, then these are given the labels A, B, C in lowercase. So excited states of different multiplicity to the ground state. So What I recommend you do now is you could even pause this video, go and have a look at the NIST webbook, so that we used in the second year. Go and look at the table of constants of diatomic molecules for dihydrogen, and you'll now start to actually understand the labelling and so on of the various electronic states in this table. So go and have a look at that. Some homework for you now is, if you go and have a look at the NIST webbook, you'll see that there's no A1 sigma state listed for H2. Have a think about why that's the case. So now we've got our electronic states, we need to think about whether we're allowed to have transitions between them, and so of course this gives rise to a number of selection rules. So the selection rules are fairly similar to what we've seen already for atoms, it's just some of the letters change. So first of all, we have delta S equals 0. So the total spin, angular momentum, is not allowed to change. So if you start off with a singlet state, you always end up in a singlet state. So this tells us that we can get singlet to singlet transitions. We can have triplet to triplet, but we can't have singlet to triplet transitions. And that's a key thing to remember when you're thinking about electronic states of molecules. The next selection rule, so is similar to our delta L rule for atoms. So delta lambda can only take the values 0 or plus or minus 1. So this means that we can go, for example, we can go sigma to sigma, we can go sigma to pi, but we can't go from sigma to delta. Draws those arrows. We can't go from sigma to delta, because sigma to delta corresponds to a delta L, delta lambda of plus 2, so that's not allowed. We have a selection rule for omega, so the total angular momentum, so the orbital component and coupled with the spin part, so I didn't say too much about that, so let's not worry too much about this selection rule, but it's the same as our delta J selection rule when we were looking at term symbols of atoms. There's a couple more for molecules. So for diatomic molecules, we've got G and U labels, so we're allowed transitions from G to U and vice versa, but we're not allowed transitions from G to G or U to U. And for homonuclear diatomics, there's an additional selection rule which says that if we're looking at a sigma-sigma transition, we can only go from sigma plus to sigma plus. We can't go from sigma plus to sigma minus, but we can go from sigma minus to sigma minus, so as drawn here on the screen. Okay, so now we've got our selection rules, so we can find our states and we can work out what transitions are allowed. So that brings me more or less to the end of this lecture. So have a look at some homework tasks, have a look at the first few low energy electronic states of oxygen, so dioxygen, decide between which states you're allowed to have transitions, and then go and complete the Blackboard quiz for this lecture. So that brings me to the end of lecture 5.